Welcome to Visual Algebra Lecture 4.7, Automorphisms. Back in Chapter 2, when we introduced semidirect products informally using our inflation method, we encountered the idea of rewiring Cayley graphs of cyclic groups. We even called this group of rewirings the automorphism group. Now that we've learned about homomorphisms, we can properly formalize this as isomorphisms from a group to itself. We'll explore automorphisms of the noncyclic groups V₄ and D₃, and we'll construct a semidirect product of V₄ with C₂. This is the first of two videos on automorphisms. The next one will focus on inner and outer automorphisms. Let's get started. We have already seen automorphisms of cyclic groups in this video series. I called them structure-preserving rewirings, and that was back in Chapter 2, in the lecture called Semidirect Products Intuitively. I strongly encourage you to watch that lecture first before this one. That said, I will make this self-contained, but it will be easier if you come into here seeing some examples. For a general group G, an automorphism is just an isomorphism from G to itself. The set of automorphisms of G defines the automorphism group of G, denoted aut of G. Back in Chapter 2, we saw the automorphism group of Zn. I called it also the group of rewirings of Zn, and that this was isomorphic to the group of units Un. This is the numbers from 1 up to n that are relatively prime to n, and the group operation is multiplication mod n. Here's an example. This is U7, so the numbers 1 up to 6, and notice how 3 times 5 is 15, which is 1 mod 7. Now, this is just a group of numbers, and the automorphisms are groups of bijections, or isomorphisms, and each one is determined by where it sends the generator 1. So for example, if it sends 1 to A, I'm going to denote that by sigma A, then it will send 2 to, so this is 2, this is additive in Zn, as sigma A of 1 plus sigma A of 1 equals 2A, so A plus A. So you can think of this map as multiplying by A. So sigma 2 is the doubling map, sigma 3, so where everything gets doubled, sigma 3 is the tripling map, and so forth. So here's the Cayley table of aut C7, or Z7, really either one, and notice how sigma 3 times sigma 5 is sigma 1, which is the identity. So if you triple and then you quintuple, that's multiplying by 15, but since you're doing things mod 7, that's just multiplying by 1. Or the doubling map times the tripling map is the sextupling map. Notice how these groups are naturally isomorphic. And also here is the formal definition of the automorphism group, is the set of sigma A's where A is in UN. We saw this picture back in Chapter 2. Notice that aut C7 or Z7 is generated by the tripling map. It's tempting to try the doubling map, but notice that 2 cubed is 8, which is 1 mod 7, so the doubling map just has order 3. If you do it twice, you double, quadruple, octuple, it's just the identity. So the tripling map has order 6 because if you triple 3 times, so 3 times 3 times 3, that's 27. Mod 7, that's -1, or 6. So you have to do that 3 more times, square -1 to get back to 1. So think of following the purple arrow as tripling. So if we replace every red arrow with 3 red arrows, that becomes here. Then to go from here to here, we replace every red arrow with 3 red arrows. So red, 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 that's doubling. Now we replace this red arrow with red, 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 that's sextupling. replace this with red, 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 that's quadrupling, and replace this with red, 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 that is quintupling. An automorphism is naturally determined by where it sends the generators. Once we know that, we can use the homomorphism property to figure out where it sends everything else. Let's do two examples of automorphisms of noncyclic groups. An automorphism of V₄ is naturally determined by where it sends H and V. There are three choices for H. Now, we can be sent to any non-identity element, and then there are two choices for V, because it can't be sent to the same thing as H, because this has to be a bijection. Therefore, there are 6 automorphisms of V₄, and I'm also claiming that all of these actually work. And therefore, every permutation of H, V, and R is an automorphism. And that should make sense. The 3 non-identity elements, it doesn't really matter which one we call H, V, and R. It's like if we have a Cayley graph and we call one of these things, let's pick an identity element, then it doesn't really matter which one of these we call V, which one we call H, which one we call R. We call this V, we call this H. That automatically makes that one R. Therefore, the automorphism group of V₄ is S3 or D₃. Let's do D₃ next. Every automorphism is determined by where it sends R and F. Since automorphisms preserve order, if phi is an automorphism, then R must get sent to R or R squared, and there's two choices for that. And F must get sent to some order 2 element, either F, RF, or R squared F. So we have 3 choices for that. Thus, the automorphism group of D₃ has order at most 6. It's not immediately obvious that we can choose both of these things freely, but it's not too far-fetched either. And by the end of this, I'll give you a proof by picture. So we can check that both of the following maps define automorphisms. So let's let alpha be the one that fixes R and it sends F to RF. So it's going to replace every instance of F with RF. And then beta sends R to R squared, or R inverse. You can think of as sending a clockwise rotation to a counterclockwise rotation, and then beta is just going to fix F. It is elementary to check that these do not commute, and in particular, alpha beta equals beta alpha squared, and so just the fact that they don't commute means that this group has to be isomorphic to D₃ or S3, because that's the only non-abelian group of order 6 or less. Now, let me give a picture for what these automorphisms mean. So here is a triangle, and there are 3 axes of reflection. And then there are 2 120 rotations. There's counterclockwise and clockwise. So it doesn't really matter which one of these we choose to be R. I might as well just pick counterclockwise. And it also doesn't matter which one of these reflections we choose to be F. So I can declare the counterclockwise direction to be R and this to be F. And what I could have just as easily called the other direction to be R and one of these to be F. So you can think of alpha as rotating the labels on the axes. Which one is, so it's going to replace each R with RF. So if this is F, then this is RF, and this is R squared F. So if we replace each F with RF, this becomes RF, this becomes R squared F, this becomes F. And then you can think of beta just as reversing which direction is the forward rotation. So this is R, but we could declare that to be R. Though that's not a proof that all of these automorphisms work, it should be a fairly convincing argument. I said earlier that every permutation of the non-identity elements of V₄ define an automorphism. These permutations are generated by a 3 cycle that I will call alpha and a 2 cycle that I'll call beta. So let's think about what this looks like in terms of rewirings. Let's start with our home Cayley graph with E in the upper left-hand corner and H being the blue path and V being the red path. So if we apply alpha, that means that the H path will turn into the V path. So that means that this blue arrow, instead of going to H, will go to V. The V path will be rewired to HV. So that means that the red path will go to HV. And then notice that the HV path, which is blue-red or red-blue, will be turned into the H path. So if you go blue-red, that takes you to H. If you apply beta, now that's just going to swap H and V. So in this case, that's going to swap red and blue. So here's blue and red and blue. Now this is not always going to swap red and blue because like over here, for example, the H path is not a color. It's red-blue. So this is not color preserving, it's path preserving. So when you apply beta to this, that is alpha beta, the H path red-blue is going to swap with the V path blue. So that means that in alpha beta, there'll be a blue path from E to H, and then there will be a red-blue path from E to V, and indeed red-blue goes from E to V. Here is the Cayley table and Cayley graph of the automorphism group of V₄ that I just showed you on the previous slide. So this is alpha squared. This is beta, alpha beta, and alpha squared beta. So once again, these are the corresponding permutations. And it's better for you to just pause this and take a look at this. There's not too much more I have to say about it, but I want you to notice that every automorphism permutes the elements of a group. So it's going to fix the identity, but it permutes everything else. And so we always have an embedding of the automorphism group into the group of permutations of G, which if we say G is order n, we say that the automorphism group of G embeds into Sn. Here, this embeds into S4, but it really also embeds into S3 because every automorphism, again, is going to fix the identity element. Now that we know the automorphism group of V₄, we can construct a semidirect product of V₄ with C2. Now, we will formalize this in the next lecture, but we saw an informal semidirect product construction in Chapter 2, and that's what we will mimic here. I said in the beginning that this lecture, I would try to make it fairly self-contained, if you haven't watched that, and I guess this is an exception, because you really do need to see this informal inflation process. But if you don't, and you should watch it, but if you don't, you should be able to follow along with what I'm doing from the context and get the basic idea. So this first factor, V₄, is going to be the group A, and the second one is going to be B. Remember, A is for automorphism, that's the group that gets rewired, and B is for balloon, that's the group that gets blown up. So we start with a Cayley graph for B, and then we are going to inflate each node into a balloon and stick in a rewired copy of A. And these purple letters, these are the labels, the labeling map that tells us which rewiring we're going to stick in which node. We have to stick the identity rewiring in the identity node. So let me do this. So we're going to stick those inside there. We're only going to do this for one of them. And then in the other node, we have to stick, if we have to stick either an element of order 1 or order 2. Because if we try to stick something of order 3 in here, like alpha, then when we do the blue edge, that means rewire via alpha, and then do it twice, we got to rewire by alpha squared. But that's not the identity rewiring, and that's a problem. So we can stick the identity Cayley graph in here, or we can stick a rewired copy. So beta is what we get by swapping the paths, which in this case swaps the colors. And then alpha beta from the previous slide looks like this, and then the other one, I think it looked like this. And then we're going to connect each corresponding node up here with, let me pick a different color for the edges, so we get this and then so forth. I'm not going to copy that 4 times. Let me just show you a picture. We start with a Cayley graph of B, and we inflate the nodes and stick in a Cayley graph for A in the first one. We're going to call that the identity rewiring. And then we apply the rewiring beta to the Cayley graph in here. And then we connect up each corresponding pair of nodes. Now, this looks like a direct product, but it's not, because notice red-green is not green-red. And if we rearrange this a little bit, we can see that it looks like a cube. So we have not actually seen this Cayley graph before, right? What do you think that is? Well, let's draw the order of the elements. So this is order 1. This is order 2, 2, 2, and then red blue is going to have order 2. What else is there? There's green blue, green blue, green blue, green blue. That has order 4, as will this, and this one at the back. Red blue green has order 2. Now, there's only 2 groups of order 4, or order 8, that are non-abelian. They are Q8 and D4, and only one of them has 5 elements of order 2. So this has to be D4. And you can see that because if you just remove this red arrow, then you have that, then what you get is basically a hexagonal Cayley graph, and we've seen that. Remember how we saw that if D4 is generated by 2 adjacent reflections, the Cayley graph is a hexagon? That's what this is. We just have an extra unneeded generator. Finally, I'll let you verify that if you stick in any of these other rewirings, you will also get V4. And one way to see that is because these first 4 things will not change. All that's going to change is how this back thing is rewired. And in both of these cases, we will get a non-abelian group of order 8. And there will be 3 elements of order 2 up here. And so there's going to have to be 2 elements of order 2 back here. And that means right away it's non-abelian and it's going to have more than 1 element of order 2, so it has to be D4. Let's now revisit the automorphism group of D3, which we saw earlier. So I'm going to call this the home state of our Cayley graphs. And remember that what this looks like is we have a triangle, and F is going to be the vertical reflection. RF is a different reflection, and this one here is going to be R squared F. And then R is going to be a rotation by 120 degrees in the counterclockwise direction. So alpha, we said, sent F to RF, and as a result, that sends RF to R squared F. Algebraically, that's just because alpha of RF equals alpha of R times alpha of F, which is R times RF, which is R squared F. So you can think of alpha as just taking every instance of F, wherever it is, and replacing it with an RF. And beta replaces each R with R squared. So that means that beta of RF is beta of R times beta of F, which is R squared F. And R squared gets mapped to R to the 4th, which is R. So let's think about what this looks like in terms of rewirings. So when you apply alpha to here, that's going to take the F path and it's going to send it to RF. So the blue path gets sent instead of to F to RF. Over here, when we do beta, so beta is going to reverse the red arrows, R and R squared. So these counterclockwise, clockwise get sent to the clockwise and counterclockwise, but it also has some effect on RF. Now, it doesn't look like it has any effect because these blue arrows are unchanged, but notice that the path from here to here is RF, whereas over here it's R squared F because the red arrows are unchanged. Now let's see what happens when we apply beta to here. So we apply beta, and that's going to reverse the red arrows. So these get reversed over here. But then look what happens to the blue arrows. So RF gets sent to R squared F. So RF is red, red. Well, let's see. Well, F is fixed. Let's do this one first. Red, red, blue, and over here, red, red, blue. It just looks a little different. And then RF is blue, and that will get sent. The blue arrow gets sent to R squared F over here. So I encourage you to check this out, and I think a homework that I usually assign is to do this with D₄. It's a little bit. I think it's a little bit more interesting. There's a few things that happen there that don't happen here. But now I want to show you. I want to do what I did with V₄ and put these in the nodes of a Cayley graph. We'll do these one at a time. So this is a Cayley graph using our first choice of Cayley graph. So this is alpha and alpha squared, and this is beta, alpha beta, and alpha squared beta. And this is the same thing, but with our other Cayley graph. Once again, this is alpha and alpha squared, and this is beta, alpha beta, and alpha squared beta. And I encourage you to check that with these rewirings, both in terms of permutations and in terms of rewirings, that alpha beta equals beta alpha inverse or alpha squared. Finally, I want to finish with several examples of semidirect products, and I encourage you to think about what groups these are. So what are the things that are being rewired and which ones are not? So we actually saw this one in this lecture. This is a semidirect product of V₄ and C₂, which is the dihedral group. What about this one? So what's being rewired here? And so we have, this is D₃ being rewired. So that means that that's the A. And the things that are being blown up, you can think of these three nodes as being C₃. So this is V₄ semidirect product C₃. At least there's some labeling map. I leave it like that. What about this? Here we have the green arrows are not changed. These things are being rewired. So this is V₄ semidirect product C₄. And finally, down here, this is, well, it looks like both of these things are being rewired. So does that mean it's a semidirect product or not? Or does it mean maybe it's a semidirect product, but then I've rearranged the Cayley graph so it's not clear as to what we are rewiring? So I encourage you to think about this. Is or is this not a semidirect product? Okay, so that takes us to the end of this lecture. And what we'll see next time are inner automorphisms. And those are automorphisms that are specifically done by conjugating elements. So these do not exist in abelian groups. Well, non-trivial ones do not exist. And in non-abelian groups, some automorphisms are inner and some are not. They form a subgroup. This subgroup is normal. It's isomorphic to G mod the center. We will understand why that makes a lot of sense using some visual examples. And then we'll look at the outer automorphism group, which is the quotient of the automorphism group by the inner automorphism group. That quotient is basically saying, what are the types of automorphisms up to conjugation? And then we'll look at class automorphisms. So there's a lot of fun stuff coming up next with a whole bunch of new visuals that you haven't seen, but I think you're really going to like. So stay with us.